Hi, my name is Yongquan Owen Hu. I'm a PhD student in the University of New South Wales, Sydney, School of Computer Science and Engineering. Today, I want to talk about the Vision-based Multimodal Interface, a survey and taxonomy for enhanced contextual system design. For this work, I'm very happy to collaborate with so many amazing people from different institutions. They are Jingyu, Xinya, Zhongyi, Shuning, Dong Samantha, Floyd, Wen, and Aaron. This work explores the intersection of multimodal interaction, human-centric systems, and adaptive and ubiquitous computing. Our goal is to analyze existing research and uncover the best strategies for building vision-based multimodal interfaces, structured by system design principles and aimed at context-aware applications. Throughout the human history, vision has been one of the most fundamental ways humans perceive and understand the world. As the dominant sense, it accounts for nearly 80% of the information we take in. Images and videos serve as the primary carriers of visual information, shaping our daily interactions. As the saying goes, a picture is worth 1,000 words, and in human-computer interaction, vision-based interaction makes that power even greater. Just like humans, smart devices need to be context-aware to interact effectively with users and their surroundings. By leveraging multimodal data from various sensors as inputs, such as visual input from cameras or audio signals from microphones, these systems can better capture environmental changes and understand user intent. Therefore, we define vision-based multimodal interfaces, VMIs, as integrating visual data with other modalities, such as audio and motion, enabling systems to interpret rich contextual information. Context-aware systems are already widespread. For example, smartphones use facial recognition for authentication, and autonomous vehicles utilize camera-based tracking to detect driver fatigue. With the rapid advancement of emerging technologies, such as large language models and wearable devices, the way we interact with digital tools is undergoing a fundamental shift. To keep pace, continuous innovation and interdisciplinary research are essential. As the figure shows, research on VMIs and context awareness has been steadily increasing in recent years, with an accelerating growth rate. Compared to existing surveys, our work presents two notable contributions. On one hand, we propose an actionable macro-micro-macro framework for system design, providing a structured approach to context-aware system construction that can be followed step by step, even by those new to the field. On the other hand, we adopt a data modality-driven approach, emphasizing the full pipeline from sensor data acquisition to processing, analysis, and high-level information extraction. In particular, our micro-level classification introduces a multimodal data taxonomy with a particular focus on visual data. First, as the core component of our context-aware system design, we initially explore key considerations of context information, including its influencing sources, human, environmental, and system factors, and its classification. We also categorize the concept of context. While our taxonomy builds on some classic works, it is adapted for VMIs, recognizing that meaning of context is inherently abstract and highly application-dependent. Second, we propose a taxonomy of multimodal data with a focus on vision. Visual data is considered separately from other modalities, as it serves as a fundamental component. We further classify it into standard vision, scale, spatial, temporal, and beyond human vision categories. To aid understanding, we present the dimensions of visual modality along with relevant examples of data types and applications. We also examine other data modalities, including speech, text, motion, and visual data, as well as the integration of different visual dimensions. We explore how these modalities are combined, processed, and utilized within context-aware systems to enhance multimodal interaction. Third, we introduced the system design foundations and outlined 4 data integration stages. To provide clarity, we presented a table comparing the benefits and challenges of each stage. We discussed 3 common multimodal data processing methods and summarized their respective advantages and limitations. We also checked and analyzed 3 common evaluation methods and quantify their use. Similarly, we present their pros and cons in a concise table. Fourth, after exploring data processing and system design in detail, we shift back to a macro perspective to examine their practical applications. We identify and summarize 9 typical application scenarios. Fifth, still from a macro perspective, we comprehensively analyzed 3 key factors: user-centric considerations, data management and processing, and system integration and resource optimization through data analysis and expert discussions. Based on this, we identified and summarized 12 current and future challenges in building adaptive and user-friendly VMI systems. Finally, we analyzed all the papers and visualized the statistical results using a Sankey diagram to support analysis and discussion. To enhance accessibility, we developed an interactive website for exploring details. The diagram intuitively illustrates the flow and distribution of vision-based multimodal data across various classification dimensions, allowing us to identify current limitations and potential future research direction. We have also provided detailed documentation of all statistical results in the appendix, including reference citations and summary counts, making it easier for users to search and reference relevant information. In closing, I would like to appreciate our all co-authors again. Please feel free to check our paper if you are interested. And we would also very appreciate if you find it is helpful and cite our work. Thank you.
Free audio post-production by alphonic.com.